Okay, so let's start. Thank you for coming for this tutorial on how to compress, compute, and conquer. And in particular, we will be talking about Python-Blosc2 for efficient data analysis. I am Francis Caldet, and me and my colleague, Luke Shaw from Iron Array will be talking about this subject today. We are from Iron Array. We are specialized in doing compression and also, in general, giving advice on how to store large amounts of data, images or whatever. So the agenda will be an introduction to Python-Blosc2, also what is the compute engine that we integrate inside Blosc2, and then how to do compute in the cloud with Caterva2, which is a companion of Blosc2, made in pure Python. So everything that we are going to talk about is open source, okay? So anyone can use it without any problem. So for the materials, just go to this URL. We have all the notebooks there. And in the README file, there are instructions on how to set up your environment. So here is the URL. And in the README, you can find how to... Essentially what we need is to install the notebook. And then the dependencies, which is essentially Caterva, as you can see here, Blosc2, and Matplotlib. So I will give a couple of minutes for you to do all the installation. By the way, how many among you have heard about Blosc before? Can you raise your hand? Okay, a few. Excellent. How many of you think that Blosc is only a compressor? So everyone knows that it's mainly a compressor, right? So during our tutorial, I hope to convey the idea that we are adding much more things inside Blosc, especially the compute engine, okay? So let's hope that you will get the idea. And Blosc2 is evolving very, very quickly, okay? We recently added also a tree store feature that probably would be interesting for you as well. If anyone has any problem with installation, just tell us and we'll try to assist. Okay. So let's go with a quick introduction to Blosc2. So Blosc2 is a package for compressing multidimensional and binary data. So first of all, why compression? Well, the first important reason for use compression is because it allows to deal with larger data sets in your desktop or laptop while using the same, or server while using the same storage. This is the first reason, number one. And number two is that under some circumstances, it can also accelerate I/O, right? So for example, if you are dealing with uncompressed data, for example on this, typically it takes a long time to be loaded into RAM, right? When in this case, into last level cache in the CPUs, right? However, if you have the same data but in compressed state, this time is much less, right? Depending on the compression ratio, of course. But in exchange, the CPU will take some time to decompress. and store that in the LLO cache. So the idea is that in some circumstances, this T1 plus T2, okay, these two times can be larger than TC1 plus TC2, right? So in that case, dealing with compressed data can be can have an advantage over working with uncompressed data. Make sense? In this case, the storage, I am referring to this, but it can be also memory. And memory is just a storage layer in the complex memory hierarchy that is common in modern computer architecture. So Blosc also leverages, well, it's a set of codecs and filters, and Blosc simply orchestrates all these codecs and filters in a way that leverages this modern computer architecture. It supports multi-threading, can automatically use modern single instruction multiple data in modern CPUs like AVX2 or AVX512 or Neon. It also has a double partitioning aspect that mimics the multi-level caches in CPUs. This is made mainly for performance. And it supports also in memory on disk or even on network storage via Ethernet, as you will see. So this is the architecture. Essentially, what we have is a series of chunks, right? So all the data sets are split in chunks with some meta layers on top. And then what we call VL meta, which is variable length meta layers, which are essentially meant for users, for adding meta information. And then every chunk is also split again in different blocks. This is why we are talking about two partitioning schema, right? So here, for example, in yellow we have a chunk that is split in blocks, right? And this is in yellow, this is the whole data set. This is a chunk, a single chunk, and this is the different blocks, okay? And as you can see, all the chunks and the blocks can be multidimensional, right? So this is something that in general no other compression package has. It, of course, all these different codecs and filters have different properties, right? So here, for example, we have different codecs in the x-axis, and this is the compression ratio. And these are the C-level ones, different compression levels, right, for different codecs. So when you combine the codecs with different filters, you will see relatively huge variation on compression ratio, right? So depending on your needs, if you prefer more compression or you prefer more speed, right? You can choose the correct combination. Although you can get very easily, it's very easy to get a little bit overwhelmed in the sense that you have many different combinations, right? But at least the possibility is there. So yeah, let's stop talking and let's get our hands dirty. So I will start. Can you hear me without the mic? Okay. So the first tutorial is a basic introduction to ND array. So first of all, let's import NumPy and Blosc2. And then let's create a big or relatively big array with 2000 by 2000 shape, and let's fill it with the results of an array. Okay. So this is it. The result, we printed the info about this array, and we can see that the shape is the one that we asked for. The chunks, you can see that the chunks are multidimensional, but also the second partition, the blocks, are also multidimensional, right? The D type, the number of bytes compressed, and the compression ratio as well. In this case, the compression ratio is huge, right? because their range is typically 0, 1, 2, which is very easily compressible. Okay? And then the C params, where you can see all the different codecs and filters that are used for creating. We haven't specified that, but there are defaults, right? So the defaults has been used. Now, let's create another, there is another way to create Blosc2 arrays, which is converting from NumPy arrays, right? So we have here this array in NumPy, and if you use as array, okay, you can convert it into Blosc2. The advantage is that this array, instead of taking, in this case, is 80 megabytes, it takes 50 times less because of the compression. In this case, we are using linear space instead of A range. This is why the compression ratio is different. Okay. Okay, good. So you can also create your own iterators and create arrays out of your own iterators. Okay. So in this case, we are creating an iterator in pure Python here, and then we use Blosc2 from iter in order to create the array with the results of the iterator. Okay. So as you can see, we created the array. In this case, see that we are using a heterogeneous data type in NumPy. This is supported as well in Blosc2, right? So all the data types that are supported in NumPy are also supported in Blosc2. So the type is here. And then the compression ratio and the C params. Okay? And these are the first rows here. Okay, of the array. So as a first exercise, I will ask you to create a 2D ND array, okay, with shape 1000 by 10,000, filled with sequential integers, okay, using the range iterator in Python. And then, instead of using the Python iterator, use the Blosc2 A range in order to do the same and compare times, okay? And we are going to discuss briefly the differences. So I will give you a couple of minutes for that. Everyone can read the font size? Yes. Okay. I suppose, oops, no problem. Oh yeah, I forgot the actual range here. Yeah. So you see, here we use the from iter, okay, and the time to create this array, it was around 1 second. And when we create the same thing with a range, we just take 75 milliseconds, okay? So this is more than 10 times faster. I suppose you will guess why, right? Whenever we are using a Python iterator, for every element that is being created, Python gets into the loop. And that slows down the computation a lot, right? On the other side, if you use a range, what Blosc2 is doing is calling NumPy behind the scenes, right? And this is very fast, okay? So whenever Blosc2 tries to do a complex thing, it tries to use ancillary libraries in order to accelerate things. In this case, it's NumPy. In other cases, it could be NumX, whatever. Okay.
So basically the same if you use NumPy range.
You use what?
No, if you just create a range and take NumPy range, would it be the same?
In NumPy, no, it would be faster in NumPy range, I would say. Yes.
I'm not sure. So using Blosc, it takes 100 milliseconds, so the NumPy takes 8 milliseconds. So I'm not sure what's happening.
Well, let me check with NumPy. I didn't try it.
Same unit is time takes MS, so sometimes you can solve them.
And then here, you need to do a reshape. But this reshape is very fast in NumPy. It's just a view. Yeah, NumPy is much faster, right?
Yeah.
Which makes sense because it is not doing compression, it's not doing anything. It's just creating the array. And the array is only 80 megabytes, so maybe it fits in the caches of the laptop, of the CPU of the laptop. Okay. Okay. So besides creating arrays, you can also read and modify. So for reading, it's just the indexing operation. Okay. You can see as whenever you do an a get item operation in Blosc2, it will always return a NumPy array. Okay, so this is the D type. Of course, you can get single elements. You can get slices. You can get multidimensional slices. Everything is supported. Also, you can set different parts of the array. Okay, by specifying. So not only get items works, but also set item as well, right? Like in NumPy. So you can set a specific part of the array, and everything will be decompressed and compressed again. This happens behind the scenes, and as you can see, we can see the modifications. Okay, so everything like this works. So, for example, it also you can enlarge the array. And you can enlarge that very efficiently. Contrarily to NumPy, that takes is a very expensive operation. With Blosc, is a very cheap operation. And the reason is because of the chunking. Okay, Blosc only needs to add more chunks to the array instead of copying the whole thing, right, in memory. So for example, this is the time that it takes to do a resize. And using NumPy, you can see that instead of 86 microseconds, it is 257 milliseconds, which is 1,000 times more than 1,000. Okay, and this is because of the chunking nature of Blosc. So having chunking has pros and cons, and this is one of the pros. You can also shrink the array. You don't need only to increase. You can reduce also the size. Also, Blosc can support data that is on disk, not only in memory. Okay. Up to now, until now, we only had arrays created on disk, in memory. But you can, for example, this array that is in memory, you can store it with the save method in this file. Typically, arrays in Blosc2 have the extension b2nd. That stands for Blosc2 n-dimensional array. Okay? And this is the size that it takes in the operating system. And then you can, of course, read the array. Okay? So this open doesn't actually load anything in memory. It just open the file from disk. And all the data is accessed from disk. Okay? So, but it behaves like a regular array. And actually, all the elements are equal.
Is this memory mapping?
No, it's not memory mapping. It supports memory mapping, but I am not using memory mapping here.
So when you access it, it will trigger the read operation and you do a get item?
Yes. All of this happens behind the scenes. Okay. And also, of course, you can create an array directly on disk without consuming any memory at all, if you want to, right? So in this case, you can pass many different parameters, but you can add this URL path here, okay? And in this case, it's an array which is it's a file that is on disk, and you can create that very, very quickly also. Okay. We can use whatever constructor, like from iter that we have seen before, and you can delete that as well. So let's have a look at the compression params. So we haven't specified yet the compression params, but there is a class which is called cparams, Blosc2 cparams, where you can specify the codec, you can specify the compression level, or you can specify the filters. As you can see, the filters is a list, okay? That means that Blosc supports pipelines of filters, up to 6. You can concatenate filters. The output of one filter will be the input of the next one. In this case, we are using only the shuffle filter, okay, which is meant for putting the bytes that have the same significance in memory together, right? And that normally improves the compression ratio quite a lot. Okay. And as we can see, we have copied this array, but changing the chunks, okay, and also changing the compression params. Okay. And we can see that we have copied with different chunk sizes and different block sizes, or different block shapes. And here we can see that we are using LZ4, that by default is Z standard. Okay? LZ4 is a codec that is meant mainly for speed, right? Not for achieving great compression ratios, but rather more for speed. Okay? Actually, I am going to suggest an exercise that you do the sum of array and array 2, okay, and compare the times that it takes. You can use just the sum method on arrays. This is something that I am introducing because in the second part, look, we talk about the compute engine inside Blosc2, right? So you can do that as an exercise. So we have array and array 2. Array 2 is compressed with LZ4, which is faster, and array is compressed with default Z standard codec. So let's do that. So sum is the reduction. Blosc also supports reduction in any access, but I am not interested on that. Okay, you see? So array sum takes, which is compressed with Z standard, takes 93 milliseconds, whereas the array compressed with LZ4, which is more meant for speed, takes half of the time. So that could be important when, depending on what you are doing, right? On the other side, LZ4 achieves only 235 X compression, and Z standard can compress more than twice than LZ4. Yeah?
Is it the slowdown of Z standard only at decompression time or also at compression time?
Z standard is using a compression time when you are creating the array, but for this operation in particular, it's a sum, it only needs to read. So we are reading from Z standard.
What I mean, my question is it slower both to read and to compress also? It's slower to decompress and compress? Or
Is it stored for compress and decompress?
The codex, is it at compression time or at decompression time or both?
No, whenever you compress with a specific codec, you need to decompress with that codec.
The question is, yes, normally like a codec is slower for both compressing and decompressing.
Okay.
Compression, when we created the array with Z standard, it would have been slower than with LZ4 as well. Normally, it's
Z standard normally is much more expensive when compressing. However, it is the default because in general compress better, right? But it's up to the user to choose one or another. Okay. Of course, you have more codecs like zlib or. There is another question. Yeah.
Is there anything in the info that refers to the speed, like the compression and decompression speed?
The compression and
The info output for the arrays. Is
Yeah.
there anything in there that indicates the speed, or is it just the
no.
inverse of the ratio?
It's a bit more. It's not just like generally it goes with the ratio, but the ratio just depends on the original data you had, and like some codecs combine better with certain types of data, even if they're not necessarily faster or slower. So it's not quite like that. It's you have to sort of know. It's more a property of the codec, and there's like some codecs which are generally faster, but it's not. There is nothing in the info.
And also it depends on the data, right? Depending on the data, some codecs can work better than others. In general, it's a complex topic, and this is why we developed also Btune, which is a deep learning tool in order to compute the most efficient combination for the user's needs. I will talk about that on Thursday, on our talk on Thursday. Okay. So yeah. Finally, let me introduce TreeStore, which is something that we have been working on for the past couple of weeks, and we are pretty happy with the results. So TreeStore allows you to organize your data sets in hierarchies, okay? Typically like HDF5 or ZAR, so something very, very similar. And then, for example, this is a way to create a TreeStore on disk. And then you assign different nodes here, okay? And you can assign meta information also on the different nodes. If we run that, we see that we created this file, which is a single file that contains all this hierarchy inside of the file. Okay? Essentially, it's a zip file. The only thing is that it can be introspected without decompressing it. So, for example, here we are reading the same file, and we can access the data and the metadata. And this is happening very fast, okay? Because we don't need to. In the zip file, it's not compressed. The only thing that is compressed is the arrays that are inside of the zip file. So you can do list, and you can also do different hierarchical operations on the tree. Okay, it's very close to HDF5 or XAR. This is still in beta, and we will have running a sprint on Friday for polishing the rough edges of that. Okay, so you are invited to join the sprint if you want. Okay, so that's all for this first part. Any question? Yeah.
For the metadata, do you have any metadata that's associated to an array, or there is only?
You can associate arrays to the metadata as well, yes. Okay. But typically you associate small arrays to metadata. Okay. If you have big arrays, normally you put that in proper nodes. Okay, good. Yes.
This codex, so the different behavior, speed versus size, and so on. Does it also depend on the type of the data? If you have like integers or floats or more regular or less regular?
That's a very good question. It's very difficult to predict that. And this is why, this is something that we put a lot of thought throughout the years that we are developing BLOSC. And this is one of the reasons, again, why I developed BTune, which is a this is a way to train a model in order to determine which would be the best combination of codec and filter and compression level for specific needs of the user. So, for example, if the user wants like very fast speed, the model will predict one combination. It prefers more compression ratio and less speed, will predict another combination. But a very important point is that the result depends also on the data, and this is why you need to train. Because depending on the data, if it's integers, or it's floating point, or it's random data, the outcome can, the ideal combination can be very different. Okay, it's not easy. It's a very difficult question. Thanks for pointing that out. Any more questions? Okay, good. So now, also tree store is also very efficient. You can see here some benchmarks that I did in this laptop, and you can see that when creating data, for example, it can be much faster than H5Py or XAR, for example, and also for reading. And the reason is we are using multi-threading very extensively, right? Whenever we can, we are using multi-threading. The content part of multi-threading is that it takes more time to set up, right? And that means that when you are accessing very small amounts of data in the big arrays, normally it takes more time because it has to set up many more threads. And also there is this two partitioning schema that makes things indexing inside more difficult. But still, the average access time is less than 1 millisecond, which is quite good. And also in the compression rate, normally tree store also is very competitive. In general, it gives the best. On all these benchmarks, I am using the same codec and the same filter, of course. Okay, I am using Z standard with compression level 5, which is the shuffle filter. Okay, so the next would be about the compute engine that Luca is going to talk about. So in the last year, we added a powerful compute engine inside BLOSC2 that allows to compute with compressed data transparently. It is important to realize that this compute engine has been made for leveraging multiprocessing. So most of the modern CPUs has many different cores inside. It's also meant to use simple structure multiple data and also to leverage cache hierarchies that can be very complex. So this is a way to do a computation. For example, we have 3 arrays here, BLOSC2 arrays compressed, and we are doing a reduction in axis 1, okay? But of this expression here. including booleans as well. All of this is supported. And as you can see, we are using standard NumPy functions here. And we can use NumPy functions because we are overriding the NumPy universal functions via the ufunc mechanism. And that means that whenever it finds a BLOS2 array, it will divert to the BLOS2 code instead of using NumPy. And this is why it can be much faster. Okay. So essentially it's a two-step process doing the computation. The first is to prepare the data. So the array typically is stored chunked in memory, and then every chunk is decompressed in multi-threading mode. And then the second step is doing the actual computation here for the chunk. Okay. So this is NumPy doing the computation here, and this is BLOS2 plus NumPy plus NumX. In general, NumPy needs to bring all the data uncompressed into the CPU, and in this case, we are, instead of bringing the data uncompressed from main memory, we are bringing the data from L3 cache, and that supposes a speed advantage. But it's better to show practically how it works. So it's your turn. Look.
Okay, so.
Do you want?
No, I think I'm projecting my voice enough, I hope. Yeah. If you go to the second notebook, which is the 02 lazy expressions, then we can get going. So there's BLOS2, when it came to the compute engine, the priority was to minimize the memory footprint as much as possible. So because you're already using BLOS2 arrays, which are chunked, this is as Francesc just explained. This means that you're not necessarily having to load full arrays in memory, which is already minimizing your memory footprint. The second thing that the BLOS2 compute engine does is it builds on that by also using lazy expressions. So NumPy would execute things eagerly, and this can often mean you end up with in-memory temporaries as you process along the computation, which is going to you're going to fill up memory, and then so you've already got the arrays, and then you've got the temporaries. So you're left with you're quite often left with not very much memory to do the computations. So if you use a lazy expression, which generates the whole computation that you want to do, and then only when you finally get to wanting an actual result does it do the computation, then you're able to save all these in-memory temporaries. So you have chunking with the BLOS2 arrays, and then you also have on top of that, you have the lazy expression, so the memory footprint can be really, really reduced relative to NumPy. Mm-hmm. So in order to get going, then we're going to generate some arrays in a similar way to we saw in the last notebook. And like I said, because we're wanting to reduce the memory footprint as much as possible, we're going to write these arrays direct to disk. So we have these two different arrays which are of different shapes. And so now we're going to create our first lazy expression. So there's two different interfaces for generating a lazy expression, which BLOS2 offers, which can be useful depending on the context. So one is this first one that's shown up here, and then there's a second one which uses a string expression. We're just going to focus on the first one in this tutorial, but in the final tutorial, this string interface is going to be quite useful. So we generate our expression, and so clearly that was very, very fast. And our arrays are very, very large, to suggest that we weren't doing any computation. And this is indeed the case, because we see the result is not an array, it's a lazy expression object. And we can print out some information about this object, including the shape and the data type. So even though we haven't done a computation, the lazy expression machinery is able to take the metadata of the operands and work out what the final shape will be and what the final data type will be without actually doing any computation and casting. And so you've already got access to all the metadata about your result without doing any computation. And well, just in case you didn't believe me about how fast it was, then there's some like actual numbers. And so the final thing to note is I mentioned that A and B have different shapes, but it's able to, well, the lazy expression is able to be defined, and it's able to work out what the final shape will be. This is because it follows the broadcasting convention that libraries like NumPy use to work out what the final shape will be from the shapes of the operands.
Sorry. Do you implement any function that have data-dependent output shapes, like the flat non-zero of NumPy or NumPy where?
Yes.
Yeah, there's.
We implement all of this.
And so how does the output shape look like in this case?
So yeah, this is for some. So what would you like as an example?
Flat non-zero, where you have a mix of zero and non-zero values, and you want to filter out all of the zero values.
Okay.
Yeah,
I don't remember. So where is
yeah.
supported for sure? I don't remember flat non-zero.
Or NumPy where, yeah.
NumPy, okay.
NumPy where?
Sort of shot.
Yeah, I mean, Blosc2 implements also the write interface, right? So whenever, and also the ufunc overloading. So whenever it has specific path code for doing things more efficient, it takes that. But if not, it diverts to the NumPy path. So probably it works. I mean, these functions will work for NumPy, but there are problems when there are two parameters. So I am not sure. I never tried this one. So it may work. It may not.
Okay. So we want to check
with where that will work for sure.
Okay. So it has returned a NumPy object.
Yeah. But you use NumPy where here.
So
maybe do you have an equivalent of NumPy where?
There is a Blosc2 where, but I suspect
it's the same thing.
It'll do the same thing. Yeah.
Okay. The problem with reductions is that reductions will always execute immediately, eagerly, which is a big difference between other kind of operations. But implemented.
It's not a reduction, it's a filtering operation.
Where is not a reduction? You are right.
It's a filter.
It's a filter, yes.
But it's a data dependent.
Yeah.
Probably yes.
There
is something that prevents the lazy expression. Yes.
Well, this is precisely the thing. Is there are some operations that you can't say in advance of doing the operation what shape it's going to be. So if I had a sum operation here, then you need to calculate to work out what the final shape is going to be, and where is something like that. So.
Yeah.
But lots of operations aren't like this. Like lots of operations that you want to do. If you want to add 1 to every element of an array, then that's something that you can use broadcast to work out what the final shape is very, very quick. Okay, so once we have our lazy expression, then eventually we are going to want a result. Like we're going to want to read out some data about what this computation actually does. And depending on our application, maybe we're going to want like a NumPy array, or we're going to want a Blosc2 array. So first we're going to look at how to get a NumPy array as a result. So one thing we can do is use the compute method, which I've got here. And then we see that the computation time is 220 milliseconds, more or less, and that we've used 220 megabytes of memory. And this is because we're outputting like we've stored our output of the computation. So the operands are on disk, but the output of the computation we've stored in this variable d, which is stored in memory. So this is why we've used some memory. But if we're wanting to reduce memory output, then maybe we would just want to write the result straight to disk. And then the only memory that we're going to need to use is as we load chunks from disk onto the processor to perform the computation and then write the result back to disk. The only memory footprint we're going to have are those chunks that we're going to load, not the full final result. So I'd like you to profile both the memory and execution time for this line in a similar way to it was done in the previous cell.
A question about memory measurement. You measure the whole memory of the whole process,
Yes.
which I find very problematic in notebooks because you always measure the whole notebook. You only need is do a stamp before and after, because this one keeps everything alive. If you use del D, it doesn't help very often because we have output history, and once you have an output, you can del as much as you want. You need to reference, but you don't need the object.
Okay.
So del is very difficult deleting objects, especially in notebooks.
That's a good point.
So you should go back to your measurement. You measure before and you measure after. So you need to have a context manager with before and after.
Within the
difference. Otherwise, you might get very strange results, especially if you keep jumping around, keep objects alive.
Okay.
You always measure the whole notebook, and the notebook itself is a few megabytes for sure already, which you measure, which has nothing to do with the arrays.
Yeah.
So just be cautious with this memory, because I did it and it can be pretty wrong.
I mean, when I was
very good point.
I did
As a context manager, you do a before and after, and the difference should be much closer to that.
Okay. I mean, I wouldn't. Okay. I don't want to mess with that on the fly, if that's all right.
Yeah. Let's continue.
I did run it a few times, and the results more or less make sense. But
It can be okay to do everything in one cell, but if you output it once and then you try to delete it, there's an output history which is a dictionary and it keeps your object alive.
Okay.
If you delete it from there, it doesn't help.
Yeah.
Because if I do reference counting, all those objects I have, instead of 3 references, I have 15. I have an idea where they come from. The notebook is doing a lot of, and every reference keeps the object alive. So delete as much as you want. Yeah. Pretty tricky.
Yeah. Good point. But at any rate, what we are trying to stress is that we are trying to minimize the memory consumption, right? Because it's something that you want to get very good speed. You need to consume as less memory as possible, and to keep it in the CPU caches as much as possible.
Fortunately, the results make sense. We're talking theoretically. This is memory. This is measuring everything as we want, as it should be measuring. Let's just say that. Okay, so we see that the. Sorry, hold on. Okay. So the first thing to note is that the computation time is a little higher, which makes sense because we have to write all the way to disk rather than just to memory. So that's what the extra time is. But we see that the memory used is a lot less. Well, quite a bit less. And this is because we're writing to the disk rather than memory, then all that we're having in memory at any point is the chunks for the operands, and that's it.
All the operations are done chunk by chunk. We never require
and we see
to load
that
everything in memory.
The final result has been written to disk with the size that we expect of 150 megabytes, which was the size of the output. Okay, this is the last exercise we want to do, which is want to compute a slice, because this is like, maybe you have a result, but it's a relatively common use case that you only want to look at a slice of the result. So with NumPy, you'd have to compute the whole result and slice it, and that's going to take as long as computing the whole result would take. But in Blosc2, we've implemented via this lazy expression machinery a much quicker way to just get a slice of the result, and hopefully you'll see that in the execution time now if you profile again the time and memory for slicing.
think it's item, no?
I
okay.
didn't. I wanted people to like.
Sorry for the spoiler.
No, it's fine. I wanted people to look at it themselves. But, wow. Okay. Well, so the first thing to note is that the computation time is a lot less than the comparable computation for the full result above, and this is because we're only calculating a slice of the result, and so what the lazy expression machinery internally does is it only looks at the necessary chunks that it needs for the final result, and only calculates the computation for those chunks. So, and then the rest of them it just skips. And so naturally, you have to do less computation, you have to check as many chunks, so the computation is faster. And because we're only notice here that we're loading the result into memory, so the result's obviously smaller, and also we don't have to look at as many chunks, so the memory used is lower, and then, of course, because it's a slice, not the full result, the total space the result occupies in memory is also reduced. So sometimes you want BLOS2 array, and especially if you're wanting to compute the whole result and write to disk, then that's absolutely you're going to want to use the compute method and return a BLOS2 array. However, you might sometimes want a NumPy array, and if you're doing that, then you use the getItem method in a similar way to we saw in the last the last tutorial. When you wanted to go from a BLOS2 array to a NumPy array, we can do the same thing with a lazy expression in BLOS2 to a NumPy array. And so that's what we're going to do here. So we'll try and profile the computation again, but we'll have to use the getItem interface. Okay. So the computation times are a little faster for NumPy because we're not having to load stuff from disk. Everything's already in memory. The computation times are faster for returning NumPy arrays because we're not having to recompress the results, which is what we had to do before because we were writing to a BLOS2 array. And then you had to decompress, do the computation, recompress. Here it's just decompress, do the computation. But on the other hand, we occupy a lot more memory when we load our result into memory because the result is no longer compressed. So, any questions?
From the first examples, so when you do the lazy expressions, you put it as a string?
There's two different interfaces that you can use. So.
Okay, so you have an interface that is closer to writing NumPy, where you can write it better than that.
And then like Francesc was saying, because it's when the interpreter gets to a BLOS2 array, it doesn't follow the NumPy route; it follows the BLOS2 route.
Yeah.
In the first case here.
Overloading the ufuncs in NumPy.
So by default, whenever I can, it does lazy.
Sorry?
By default, BLOS will do lazy operation whenever it can.
Yes.
Unless you do an aggregation, in which case it switches to NumPy.
Yes.
And when you get a lazy expression, you need to use the get item or the compute, depending on what you want.
And then, yeah, so basically any of the functions that you can think of in NumPy are supported in BLOS2 because of this use of the ufunc interface. So we can go and define any sort of expression, and the lazy expression will be generated, and then we can either use the compute or the get item method and get the result that we want on the lazy expression. Okay. Right now I'm going to do a more demanding example so that BLOS2 really, you can see how much better it can be than NumPy. So on the version on the GitHub repo, we put n frames equal to 100 because otherwise NumPy just falls over on a conventional laptop. But I'm running on a server that's got 32 gigs of RAM, so I can make it a bit bigger. Okay, so we generate some data, 3D data, and then we're going to try and do a lazy expression on that data, and going to try and plot it. So, first thing I'd like you to do is profile the memory usage of this expression here. Okay. So the main point that I want to point out, or the main thing I want to draw your attention on, is we can chain together multiple different functions and expressions, including using NumPy functions, and because it recognizes that the operands are BLOS2 arrays, it'll still generate a lazy expression, and it'll do so very, very quickly without doing anything in memory, just the lazy expression. And you can still access the shape and data type very quickly, all this metadata. And we see that the result is going to be close to 8 gig. So if we wanted to try and load that, so the operands are already quite big, and then in addition the result is going to be 8 gig, so we're quickly going to run out of RAM. And so if we go here, then we can, what we're doing here is we're generating on the fly, frame by frame, a calculation of the result. So we take our lazy expression and then we ask it to compute with the operands, and so it'll load the necessary chunks for the frame that we want to see, and it'll go and then render it. And if you think this is slow, then I can say that it's not slow because of Blosc, it's slow because of matplotlib, because if I comment out this line, then it's not going to do any computation.
Matplotlib has to do a lot of work
to
do the animation.
Matplotlib does the animation, and you'll see, so with the computation it took about 20 seconds, like 20 and a half seconds, and now it's going to take something like 18, 19. Yeah.
It's going to be 20.
Almost the same. So the computation isn't really adding on any time. Blosc2 is very, very fast. I'm sort of running out of time, so I'll skip this exercise for you guys, and we'll just directly compare NumPy and Blosc. So what I can do is I can use this monitor function, which I've already written. It'll profile Blosc. Oh, sorry, hold on. It'll profile Blosc2. And then I can do it again. I can profile NumPy. So it's already taking longer. I'm getting quite impatient. So it took about double the time in NumPy because you had to load all the operands into memory, and then we had to do all the computation in memory. And so quite quickly ran out of. This is with 32 gigabytes of RAM. We quite quickly ran out of RAM to do the computation efficiently. You see, if we had even bigger operands, even bigger results, then Blosc2 would get even faster relative to NumPy.
So you can think about lazy expressions as a way to express your complex operations in a very efficient way, and you can get only the important information that you are interested in without the need to evaluate everything, right? Only the slides or the item that you want.
And of course, if we only wanted a slice of the result, then Blosc would be even faster, because NumPy is going to calculate everything, regardless of if you only want a slice, and Blosc is only going to calculate only going to use the necessary part of the operands to get the final result. Any questions? Okay.
Good.
So we'll just move on to the last part, which is going to be. Presentation mode.
You can maximize, maybe that would be enough. I think it's it can be seen quite easily.
Okay.
You can do the introduction. You are doing it very well. So.
Okay. So Blosc. So we talked about Blosc2, which started out just for compressing arrays. Then on top of Blosc2, there's been a computation added to really take advantage of the chunking, and then IronArray also. I've got another open source library, which is pure Python, which is Caterva2, which is designed to build on Blosc2 to work with remote arrays. Because what's the problem with remote arrays? Well, you have all your data stored on a server, and then you want to try and compute with that data. And so if you don't have any way to really ask the server to do computations, you have to try and load the data onto your laptop or some sort of local machine and to do the computation. And that's fine if you're working with small data, like 10 megabytes. If you've got 10 gigabytes, if you have a big computer, you've got like a decent desktop, then that's possible. Once you get to like 10 terabytes, which we have Cyclotron clients who work with that sort of level of data per day, then it's not, that is not happening.
More than per day, probably per minute or per second. It's crazy. The synchrotron.
It gets more every year because everything gets higher resolution. input-output gets faster. So if you're trying to work with 10 terabytes, then you need to do something because you can't load it onto local machine. In addition, one, because you haven't got the memory to be able to compute with that, and two, because the amount of transfer time to send the 10 terabytes from the server to some other machine is prohibitive. So the idea is like, well, if you already got the data on the server and it fits, then why don't you just do the computation there, where the data is, and then send the results to your local machine if you need it. And this can be very efficient. Consider if we've got a very large data set, and you want to calculate the sum of the whole data set. Well, then it's clearly, if you've got a server with reasonable number of computational resources, it can calculate the whole sum, and then it just reduces the 10 terabytes to one number, and then the one number can be transferred very, very, very quickly to your local machine to read out. That's a very extreme case, but you can imagine, okay, maybe you want to calculate the sum over a couple of axes of the data. So instead of 10 terabytes, it's now a gigabyte, and that's, again, it's reasonable to send that to your local machine. So this is the kind of logic behind Caterva2. And so the idea is to have Caterva2 as a link between your local machine and the server, and have Blosc2 as the kind of workhorse on the server that works with your arrays and does all the computation. So that's the big idea. How's it implemented? Well, so you have a user running Caterva2 on the machine, and then you kind of access the server through. We offer a range of different APIs depending on user level. So some people really like to work with the command line. Some people really don't like to work with the command line. So they maybe want something else. So we've got a web interface, which is for minimal user level, and then there's also a notebook interface that you can use via notebook, which is a bit more programmatic. And then on the server, which is running Caterva2, we've got kind of all the machinery, and we offer support for Blosc2 arrays, but also HDF5 files, because these are very common file types. Okay, so if you want to find out,
an important thing is that all the data is transferred in a compressed state.
Yes, I think we forgot to mention that because we always store things compressed to make sure you're not using up unnecessary storage on the server, and then it's also sent compressed so that you're maximizing the file transfer time, which is typically. So typically metadata is transferred in JSON form, which is more than enough. But for a large being more than 1 megabyte or more than 1 kilobyte, everything is compressed through the wire, okay, between the server and the client. And so we've got, like I said, Caterva2 is all open source. It's on the Iron Array GitHub, so you can go and have a look at it. You can download it, and you can set up and run. If you've got your own server, you can download it and run it on your server. If you want to find out more about how Iron Array can support you in that process, then you can look at our website as well. Okay, so let's do the last of the tutorials. We've got 20 minutes left. Sorry.
So Caterva2 is the free software. We also offer a commercial software, which is Cat2Cloud, where we install everything in a server where people can use it. Okay, it is currently in beta stage. Okay, and you're invited to test it if you want.
Okay, so first we need to connect to the remote server, which is this URL, which is a demo that we have running, which has data sets stored. So this is the web interface I mentioned that you can interact with the data. But this is the server and the data that we're connecting to here in the notebook. And so that's the cat2 card demo, and then the root that the data is stored in is the public root, and then these are the names of the data sets. So I mentioned that like Caterva 2 is really what you want to be doing for working with remote data sets. There's a very limited or somewhat limited functionality for working with remote data offered by Blosc2, which is here, and so you can set up a local reference to a remote array with Blosc2. And then, so the local reference won't download anything. It'll just point to that data on the server. So consequently, it's very quick to generate because it's not downloading anything, and it does not occupy much storage or memory space because it's just a point. But we can still it's got some metadata about the remote array, which we can access very quickly. So, for example, we can look at the compression ratio if we wanted to of the remote array, which in this case is roughly 10. Okay. So, got time. So, first thing we're going to do is print out the shape and number of bytes of the data sets. So, we can access the metadata of the like so. Then, if I want to get the number of bytes of the data uncompressed, I have to do a little workaround.
Let's not forget that this Python API runs on top of the REST API, right? So that means that you don't need Python. You can use whatever language you want, for example, JavaScript, in order to access the REST API. The only thing is that the Python API is much easier, of course. Yeah.
About the tree storage. Now, if I use HDF5 with PyTables, and I have this new tree storage in a zip file, what are advantages, disadvantages of using? Can I combine these, or?
No, you cannot combine. It's a different format.
Different format.
Yes. So, tree store stores in a specific format for Blosc2. It's an extension of the Blosc2 format, right? It currently only lives in the Python space. We haven't not translated that into the C library behind the scenes. Whereas HDF5, everything is encoded with C, right? And then, also the container for the Blosc2 is a regular zip file. The only thing is that it works in store mode, and store mode means that it doesn't compress anything. So there are not double compression. There is of Blosc2 and on top zip. Zip is only the container for storage, okay? But it's completely different from HDF5. Yeah.
So with HDF5 you have tables, and you have indexing to things.
HDF5, sorry?
You can have a table with columns,
yes,
which is different because this is for arrays, yeah. And
no. In HDF5 you can also have multidimensional arrays.
I know. Yeah. But one important storage is to have a table you can have an index, like you can get a sort inside?
Yes, with PyTables you have indexes, and the access is much faster. But this is specific for PyTables. This is not. For HDF5.
If I only use NumPy arrays, this is kind of very equivalent to
Exactly. If you only use NumPy arrays, or even if it is a heterogeneous data types, like tables, for example, you can use tables also in Blosc2. Yes.
Yeah. It's easier. You don't have to install another C library. All this.
Exactly. It's only one single dependency. Also, we decided to support HDF5 in Caterva too, because in the cloud, there is many times that you cannot afford to convert HDF5 to Blosc2. So you want to use HDF5 natively in the cloud. This is why we added support for that. One of our customers is a big user of HDF5, and they wanted to use that strength to the cloud.
Wrong slice. So. Okay. So the first thing I want to point out was if we access our arrays, we can get the metadata. If we look at the type of the arrays, then they're C2 arrays, and this is the type of a local Blosc2 reference to a remote array. And then we can download references we can download data from the array using slices like this. And this will take some time. And then finally we can perform computation, I should time this computation as well. I think it's caching.
Don't worry.
Yeah,
just explain that it's caching.
Yeah, sorry. It's.
Yeah, the idea is that you can convince Caterva 2 to do all the operations in the server instead of bringing the data into the client.
But yeah, sorry. The point is that the computation will be performed locally on the local machine. So I define the Blosc2 expression, and then I ask it to compute, and so it'll download the necessary chunks from the server and perform the computation locally. So this is maybe all right if the arrays aren't too big. If the arrays are very large, this will start to be a problem. So one solution to this is like I said, is Caterva 2. So we do all the computation on the server, and then we download the result from the server. So the first thing we have to do is we have to somehow connect to the server, and the way you do that in Cateva2 is you define a client instance, and then via that client instance you can access the directories, or as we call them, routes, that are on the server. So we're going to access the route, which we already said is the public route, then we're going to try and access the data sets. We see again it's very rapid, and again we're not downloading anything, so that's why it's so quick. So now let's have a look at what our local references, which I've stored in these two different variables, what these local references are like, and what sort of information we can access quickly. So just do a similar sort of thing to above.
Yes, a remote dataset.
Okay, so it's the same size because it's the same data set, but the class of our local reference is different. It's not a Blosc2 C2 array; it's a Cateva2 client data set. Again, it's a local reference which points to the remote data set. We can still interact with it in the same way. If we want to download a slice, then it's very simple. It just accesses the slice and asks it to be sent compressed. Asks the necessary chunks to be sent compressed over the network, and then decompresses it locally and returns the slice you've asked for into the variable. So very quickly, I'm going to.
Only a couple of minutes.
Yeah, I've only got a couple of minutes left. So against the clock. You want to calculate your lazy expression. So you have to get. So, well, the first thing that I've done here is I've defined a lazy expression on the server, because that's where I want the lazy expression to execute. So that's like the first difference. The lazy expression is not defined on the local machine, it's defined on the server. So now I need to try and speak to that lazy expression on the server. And the way I do that is using this method. And then I can access metadata about the result. for example, the shape, like this. Oops.
The dot.
Yeah, sorry. Okay, so the lazy expression, my local reference to lazy expression can access lazy expression on the server, which uses the Blosc2 compute engine to use the metadata of the operands on the server and calculate determine the shape of the final result all very quickly. Okay, so now what we're going to do is we're going to compute the expression on the server. Oops, sorry.
You need the indexing operation for.
Yes. Sorry. So So now what we asked it to do is we've asked it to calculate the expression on the server. It then does that, compresses the result, and then sends it to our local machine. So you can see that this could be quite a bit faster than the Blosc2 case, because in the Blosc2 case we have to have to get all the operands and compute locally. So if we consider the example I had before of the 10 terabyte data set, trying to calculate the sum, and clearly it's much better to calculate the sum and then send one number than send 10 terabytes and calculate the sum locally. That's going to be a lot quicker. And then this is a bonus because I suspected that we weren't going to have time, as indeed has been the case. That is something you can have a shot at home, is to set up your own server on the local machine.
Okay.
Which, might be interesting.
Thank you, Luke. So yeah, we have scratched. So we scratched just the surface of Caterva 2 and Blosc2. You want more information? We will have a talk on Thursday, okay? And we will be around for all the conference. So if anyone wants more talking or interested in whatever thing, so just let's have a chat, okay? So thank you very much for your attention, and talk to you.
If everyone has questions, I guess you can come up afterwards, just because I'm sure everyone wants to just go. So.
Okay.
I have a quick question.
Go ahead.
Sure.
So in Blosc2, when you do the lazy operations, for instance, you do multiply plus A plus B plus C, and it does fuse the different operations so that it doesn't move intermediate results out of last table cache?
No, so all the intermediate results are evaluated chunk by chunk. So you will create temporaries,
Chunk by chunk, okay.
but only chunk by chunk. Even more, the temporaries are evaluated via numexp if possible, right? And numexp splits again the chunks in sub chunks or in small blocks, right? And the only temporaries will be these small blocks that typically fits in L1 cache. And this is one of the reasons why temporaries typically never go into the memory. Typically they stay typically in L1. This is the secret for performance.
Does numexp generate a small program? Does it compile?
numexp is compiling on the fly, yes. It can generate a small program. But this is very fast and happens behind the scenes. Yes. Yeah.
I'll tag in another question. Yeah, thanks for the talk. I was wondering whether this sort of, a lot of what you're mentioning kind of resonates with the geoscience community, but I think their approach is quite different in terms they use ZAR and then loading that into Dask arrays, and ZAR has loss compression, and then there's also the capability of scaling that out to multiple Dask clusters horizontally.
Mm-hmm.
I was looking at some comparisons on your website about performance, so I think that it's interesting to see you guys compare that as well.
Mm-hmm.
I was just wondering, have you considered I guess, and part of what you mentioned as well is the tight integration between the Blosc compression and actually like the computations.
Yeah, exactly.
Right.
This is very important.
Have you considered contributing that towards Dask, or like how does that fit in the ecosystem? Would it be possible to kind of bring that into the Dask ecosystem, or is that something you considered, or is it like fundamentally different? Of course,
totally we considered collaboration with, especially with the ZAR with the ZAR guys, and actually ZAR supports only Blosc1. And we moved to Blosc2 like a couple of years ago, and I tried to send an implementation for the Blosc2 codec in ZAR, and I filed a pull request, but nobody answered, right? So I don't know. we try to be open and we try to be collaborative, but probably they have other priorities. I don't know. Okay, but of course we think. I mean. We think if you want to do computation very fast, you need to integrate very well with compression.
Yes.
This is absolutely key for getting performance.
Yeah. Cool. Just want to
and for Dask, I mean, the Dask approach is quite different. I mean, Dask tries to be like a very general compute engine for NumPy, for pandas, for many different things. I think we are different worlds, right? We are more focused on compressed data, and they are more like a very general thing. But of course, we are open for cooperation if necessary as well.
Thanks.
Mm-hmm. Any more questions? Well, it's time for some dinner, probably. Okay. Thanks again.
Yeah, thank you very much.